Hello everyone, I'm Hamsong, and let's do the second question of homework 12. And first, let output be yt equals yft plus ynt. And and since r square, the signal over noise square equals ift0, the magnitude square over e of ynt square. And this one equals to 1 over 2 pi, the sum from minus infinity to infinity, yf omega e to the j omega 0 d omega the magnitude square, and this one equals to 1 over 2 pi, the sum from minus infinity to infinity, syn omega d omega the magnitude. And in order for this one to be maximum, we need to make this one to be maximum. So this one, and since this is a LTI system, so yf omega equals to h omega times f omega. And according to Schwamm's inequality, according to notes, this one can be this one is smaller than the product of these two, h omega's magnitude square, from the sum from minus infinity to infinity times f omega times e to the j omega t0, the magnitude square. And since e to the j omega t0, the magnitude square equals 1, so the product of these two equals this one. And after get the maximum value of the above part, for the bottom part, this one will equals to Sn omega times h omega's magnitude square. Here we let Syn omega equals Sn omega times the magnitude of h omega square. And this is also a equation from the notes. So this one finally equals the sum from minus infinity to infinity h omega the magnitude square d omega, since Sn omega equals 1. So we substitute this one and this one into this formula. We get that r square is smaller than 1 over 2 pi square, the sum from minus infinity to infinity h omega the magnitude square d omega times the sum from minus infinity to infinity f omega the magnitude square d omega over 1 of 2 pi the sum from minus infinity to infinity, the h omega the magnitude square d omega. And since this one and this one can be cancelled, and this one and this one can also be cancelled, so the final result is the sum from minus infinity to infinity f omega the magnitude square d omega over 2 pi. And in order to reach this maximum, according to Schwamm's inequality, h omega must equals to k times f omega times e to the j omega t0, the conjugate. And this one equals to k times f omega the conjugate times e to the minus j omega t0. So we get, since ht and capital H omega is the formula transform, capital H omega is the Fourier transform of ht. So ht is equals to k times ft minus t0 the conjugate, and we let t equals to 1. Then ht will equals to f t minus t0 the conjugate, and we have proved it. And we for the response filter ht, we first let ft let the graph of ft like this. The value is 1, and this is from 0 to t. So when ht equals to f capital T minus t, the graph is like this. Firstly, ft will be slipped into the other side of the axis, and then slides capital T units, so it just left unchanged. And for ht equals f t capital T over 2 minus t, the graph will be like this. Since in this case ft is real, so the conjugate of ft minus t0 is just equal to ft minus t0, and when ht equals f 2 capital T minus t, the graph will be like this. First it will flip into the other side of the axis, then slides 2 t units, and then it will be like this.